guys, welcome to lesson 9.7. We're going to learn how logarithms can help us solve exponential equations. We've already solved exponential equations back in Unit 8. You don't need to write this part, but back in Unit 8 we learned how to solve equations kind of like this. We had like maybe 4 to the x power equals 32. And what we would do is we would change the bases so they matched. And then we would drop the bases out and solve what's left. Okay. The problem with that method is that it's extremely limited. You can't always get the bases to match like that. And in those cases, the only way to solve them is with logarithms. And that's what we're going to look at today. So let's go ahead and get started here. Number 1. Today, the odd ones are going to serve as teacher examples, and the even problems will serve as student practices. So there's no way, for instance, on this problem for me to get these two bases to match. That's just impossible. So what we're going to do is we're going to do something called logging both sides. So whatever number has the x as its exponent, you're going to log with that base on both sides. So to get rid of the 18, I'm going to log with a base of 18 on both sides of this equation. Okay, so all I did was I just put a log base 18 on both sides. And the reason for that is because we have a log property that says that this just cancels each other out. And now all I have to do is use my change of base formula here to figure out what x equals. So I would have log 79 divided by log 18. And if we use a calculator, we will get 1.512. And that's it. So step 1, log both sides. Step 2, change a base. All right, so let's go ahead and have you guys try one of those. Pause the video here, and when you unpause it, you will see the solution. So for number 2, you should have gotten 1.9243. Go ahead and move on to the next question. The next question we're going to look at, basically we're just going to be gradually increasing the level of complexity of the problems, but other than that, not much news going on. The main step is just logging both sides, so long as you know how to do that, you're in good shape. So in this case, the number that has a power on is the 18, so that's what I'm going to log on both sides. I'm going to do log base 18 on both sides of this equation. So these cancel out, and it leaves me with 5p minus 4 equals log base 18 of negative 79. Okay. Now, at this point, I'm going to stop and say no solution. And that's because there's a negative there. Logs can't have negatives in there. So this is a no solution type of problem. Now, just for the heck of it, though, because your problem probably won't be like this, I'm going to pretend that that's not negative. Don't write this down on your notes, please, because otherwise you'll think this is what you do in your notes and you don't. But I do want to show you this because when you do your student practice, you're going to be able to actually finish the problem. It's not going to be a no solution problem. So in this case, let's make that 79 a positive. So if you can do it, then go ahead and just keep going like usual. You would do your change of base. Get your trusty calculator out and figure out what that is. And once again, I get 1.512. And from there, just go ahead and solve it like normal. You would add 4 on both sides. And then you would divide both sides by 5. And you would have your final answer, which is 1.102. Okay, but like I said, on this problem, we're actually not going to be doing all of this because I have no solution because there's a negative there. But on your guys' problem, like I said, you probably will have a solution, so you're going to keep going with the steps that I just showed you there. So let's go ahead and have you guys try one here. Go ahead and pause the video and give number 4 a try, and when you unpause it, you will see the solution. So you should have gotten 0.4457 for that second problem of yours. Let's go ahead and move on to another example. Number 5. Okay, so what makes this one a little more complicated is that there's a lot more than just an exponential expression here. We have extra stuff going on. We have, this is my exponent part, and the rest of that, the -7 and the -10, those are things that I want to get out of the way. So if you have extra stuff, what you want to do first is you want to get the exponential part by itself. And by exponential part, I mean the a to the x stuff by itself. So to do that, I'm going to start by adding 10 on both sides. Oh, I just got ahead of myself there. So those cancel. Next, we want to divide this -7 out of the way. And 80 divided by 7, that's going to be a decimal, so we might as well just use our calculator here. It's going to be 11.429. Then we're going to go ahead and from there solve it like we did the last problem. So I'm going to log base 10 on both sides. And when you do a log of base 10, you don't really need to write the base. Also, another cool thing is you don't have to do change of base either when you have a base of 10, because our calculators already have base 10 on them. So this, I don't need to do change of base. I could just push log 11.429 and get my answer. Now, when you guys do your problem, it probably won't be base 10, so you'll probably have to do the change of base to get it to work. From there, we're going to go ahead and add 7 on both sides. And then we're going to divide by -9. And I'm getting -0.895. Okay, so the real point of this exercise here was these first few steps where we get the exponential piece all by itself by adding and dividing. The rest of it is pretty much the same as what we've been doing. So go ahead and pause the video here and give this one a try. And when you unpause it, you will see the solution. So the answer to that one should be 0.1848. Go ahead and move along. I'm going to revisit some word problems that involve exponential functions. So first of all, if you have just a general exponential problem, I'll just title this general. They look like this. Y equals A1 plus or minus, depending on whether it's increasing or decreasing, r to the power of x. Okay. If you have compound interest problems, they look like this. And then if you have continuous growth problems, they look like this. I'll go with Y on this one. Okay. All right, let's go ahead and take a look at number 7 here and see which one of these formulas we're going to use. So In 1980, the population of Mexico was 67 million people. Since then, the population increased by 2.5% each year. How long will it take the population to reach 70 million? Since there is no word in here, it doesn't say compounded, and it doesn't say continuous. So it's neither one of these. It's the general formula. It's this guy up here. So I'm going to use this. Now, when you're doing the general formula for compound growth, for exponential functions, this is your growth rate, which is a percentage. But you are going to change it to a decimal by dividing the percentage by 100. Okay? And then this is your starting amount. Now, this is if your function is increasing, and it's minus if your function is decreasing. So, reviewing all that, let's go back to the problem now and see what we got. We see that there's 67 million people. That is our starting amount, the A value. Here's my R value, but remember, that's a percentage, so we need to divide it by 100. That's my R value. And it says that the population is increasing, so we're going to go with the plus. Okay, so setting this up then, we would have the following. We would have y equals 67 million, 1 plus 0.025 to the x power. Oh, and I forgot, actually, there's another number here. Should have included that. 70 million, that's my final amount, and I didn't label that here. But y would be the final amount, okay? So 70 is my final amount of the population. So the population starts off at 67, it ends off at 70 million, and the growth rate is 0.25, and it's increasing. My goal is to find x, and that will be how long it takes for them to reach. X is the time in this case. So let's go ahead and simplify it first of all. We have 70 equals 67 times 1.025 to the x power. Now I want to solve for x. That's going to tell me how long it took to reach that value. So the first thing we're going to do is we're going to get rid of the outside numbers, right? The numbers that are not part of the exponential. Here's the exponential piece. So I want to get rid of that 67. So I'm going to divide both sides by 67 first. So 70 divided by 67 is 1.045. Now, I want to cancel out this 1.025 so I can get x by itself. And to do that, we're going to log both sides. And when we do our log on both sides, we're going to use a base of 1.025. So I just put a log with a base of 1.025 on both sides. On the right side, these cancel out because they match. And now we need to figure out what's the answer on this left side. And to do that, we're going to do change of base. So we're going to do log of 1.045 over log of 1.025. And punching that into our calculator, we should be able to get a nice answer. So log of 1.045 divided by log of 1.025 is about 1.783. And this is in years. The question was how long. So it would take about 1.783 years for the population to increase from 67 million people to 70 million people when it's growing at that rate. Okay, so there it is. So step one is to decide which formula you're using. Step two is to plug all your numbers into that formula. Step 3 is to go ahead and solve the equation for x. All right, let's go ahead and move on. Let you guys try one of those. All right, so go ahead and pause the video here and try out this problem. When you unpause it, you will see the solution. All right, so step 1, it's a general formula. It's not a compound interest formula or a continuous growth problem. Our final amount is 100. Starting amount is 200. We are decreasing by 11.5%, or in other words, 0.115. And then simplifying it, we get this. So there's our formula. Now I want to start solving for x, which will tell us how long it takes for the C14 to decrease from 200 milligrams to 100. So how do we do that? First thing we do is we're going to divide both sides by 200, which gives us this. And then from there, we will log both sides with a base of 0.885. And then from there, we get this as our answer for x, but we need to turn that into a meaningful number to us. So we do change of base, and we end up with 5.674 years. All right, let's go ahead and do one more set here. Number 9, caffeine leaves the body at a continuous rate of 17% per hour. How long would it take the amount of caffeine in your system to reach half of its original amount? Okay, so notice it says continuous, so that means we're going to be using this formula. Oops. All right, this is the final amount, once again, same idea there. This is the starting amount. And this is your percentage, which, once again, you need to divide it by 100. Now, if you're increasing, then we're going to make it positive, and if you're decreasing, we're going to make it negative, and you just have to do that yourself. It's not part of the formula. And then up here, of course, is the time. Okay, so that's our formula, and that's the continuous growth problem. So on this problem, they're telling us our R value here is 0.17, and the caffeine is leaving the body, so it's going to be decreasing. So my R value, if I put those two things together, is going to be a negative 17 over 100, which is negative 0.17. So there's my R value. After that, they don't tell me anything else. That's not enough information. So we have a problem. Now I want to find T, which means that they need to tell me what R is, which they did, but I would also need to know P and Y. E is not a variable, so we already know that's just a number. That's 2.71. So we don't need to know that value. We already know it. But the problem is P and Y, and this is a weird problem because of how they're telling you something. They ask, how long will it take for the amount of caffeine in your body to reach half of its original amount? Okay, so this is kind of like going to be a little tricky thing, so pay attention here. We have PE, R is negative 0.17, T. The final amount is half the starting amount. So if this is my starting amount, then half of my starting amount would be 0.5 P. Or you could just say half P, like 1 over 2 P. But I prefer decimals, so I'm going to do 0.5. And I'm preferring decimals because all these problems end up being decimals anyway. So that's kind of a weird thing. We don't know our starting amount, but we do know that the final amount is half as much as the starting amount. So that's kind of a weird little twist on the word problem here. But let's go ahead and get to solving. So the first thing we can do is actually get rid of that P that we don't know right away. It doesn't even matter. It just kind of disappears. And then from there, we're going to log both sides. We're going to do it with a log of base E. And as you guys may know, when you do a log of base E, that's an ln. So these cancel each other out, and I'm left with negative 0.17t. And on this side, we don't need to do change of base for that because our calculators have an ln button. So I can just push ln of 0.5, and I get negative 0.693. So to solve for t, the last thing I need to do is just divide by this negative 0.17, and I'll have my answer. Which is 4.077. And it looks like it's in hours is the time we're measuring here, so it would take that many hours. So there it is. So a couple of new things here is we're using the continuous growth formula. Another thing is they didn't tell me my starting amount, but they did tell me that my final amount is half the starting amount, so we did this little trick here with the p's. From there, we just solved it like normal, but we did end up with an ln this time, which is what's going to happen anytime you have a continuous growth problem. All right, let's go ahead and have you guys try one of these. Now this thing says compounded and it says continuously. So which one do you use? Use the compound or use continuous? You're going to use the continuous one. So you guys use the same formula that I used on number 9, just so you know. The compound interest formula is only for problems about interest growth. Anyway, so go ahead and pause the video, give this one a try. When you unpause it, you'll see the solution. All right, so continuous growth formula. Once again, this is another problem where they did not tell you the starting or the final amount, but we do know that whatever the starting amount, the final amount in this case is twice as much because they're asking how long it would take to double. So my final amount would be twice as much as my starting amount. Notice also I've got a positive R value here. This one might be a little bit difficult for you to see why, but when you're talking about interest rates, they're always adding the amount in when it comes to interest rate problems. They're never taking the money away. So it's going to be a positive 0.01. If you divide both sides by p, you're left with this. And then we want to cancel out the e, so we natural log both sides, and we end up with this. These cancel out, leaving us with this. Using our calculator to simplify that, we get 0.0693, and then dividing both sides by this negative 0.10, we have our final answer of 6.931. Right? And there it is. So that's how logarithms can be useful to solve more complex types of exponential functions, which we started looking at in Chapter 8, but now we're finalizing it in Chapter 9. So that's it, and we'll see you guys in class. Have a good day.